Who is Saz? What is your full name? Can you hear me?
Yes, sir.
Uh, Rename yourself.
My name is Supratik Majumdar.
Who is Saz?
Saad is Sahnawaz
My name is
Alam.
Shaniaz Alam, sir.
You have to give your full name according to your
Okay.
university. Okay. Every
Okay,
time
next time
when
I will give full name. Okay, sir.
Okay. Is this visible?
Yes, sir.
Yes, sir.
Okay. So last day I have discussed about some CVD techniques, the Sparta deposition techniques, etc. And today, now I will discuss on diffusion. Okay. So diffusion is a process basically to introduce a controlled amount of dopants into semiconductors. Okay. And to alter the conductivity type. Okay, in the actually in the diffusion process the dopant atoms are introduced from the gas phase or by using doped oxide sources. Okay, the doping concentration decreases monotonically from the surface, and the in-depth distribution of the dopant is determined by the temperature and diffusion time. Okay, so so diffusion basically it is used to form a deep junction such as an n-tub in a CMOS device. Okay, so diffusion in a semiconductor, actually what happened, so in semiconductor that can be envisaged as a series of atomic movements of the diffusion or dopant in the crystal lattice. Okay, so here are two pictures which illustrates the two basic atomic diffusion mechanisms. Okay, one is the vacancy diffusion and another is the uh, interstitial diffusion mechanism. Okay, so here the open circle, this represents the host atoms occupying the equilibrium lattice positions, and the solid dots, these solid dots represent impurity atoms. Okay, now at elevated temperature the lattice atoms vibrate around the equilibrium lattice sites. Okay, so there is a finite probability that a host atom can acquire sufficient energy to leave the lattice site and to become an interstitial atom, thereby creating a vacancy. Okay, so when a neighboring impurity migrates to the vacancy site like this one, uh, this mechanism is called the vacancy diffusion mechanism. Okay, and if an interstitial atom moves from one place to another without occupying the lattice site, This mechanism is called the interstitial diffusion mechanism. Okay, so basically this can be determined by the use of Fick's law. So here this is the first law, Fick's first law. The basic diffusion process of impurity atoms, uh, that is similar to the that of the charge carriers. Okay, now if assume the F, that is that will be the flux of dopant atoms traversing through a unit area in a unit time, then we can write it this equation as F equals to minus D delta C by delta X, where D is the diffusion coefficient, C is the dopant concentration, and X is the dimension uh, distance in one dimension. Okay, so this actually this is the fixed first law, and the equation actually imparts that the main driving force of the diffusion process is the concentration gradient. Okay, so this is the concentration gradient delta C by delta X. In fact, the flux is proportional to the concentration gradient, and the dopant atoms will diffuse from a high concentration region toward a low concentration region. Okay, and here the negative sign on the right hand side of this equation states that matters flow in the direction of decreasing dopant concentration, that is the concentration gradient is negative. Okay, now according to the law of conservation of matter, the change of the dopant concentration with time must be equivalent to the local decrease of the diffusion flux in the absence of a source or a sink, and thus we can write it as this equation. Okay, so we can write it in this type of equation, and from this equation actually this is when the concentration of the dopant is very low, the diffusion constant at a given temperature can be considered as a constant. Okay, and this equation can be rewritten by this one. Okay, and that is this equation actually it's a general diffusion equation. It is used as, this is the fixed second law of diffusion actually. So it's a partial differential equation for n number of atoms into x t. Okay, now to find a particular solution we will need to specify certain initial condition, and we can find out it as in this way. Okay, so clear up to this much?
Yes, sir.
তীর্থম সামন্ত, তীর্থম সামন্ত
ও ঢুকে গেছে কিন্তু ও বোধহয় নেয়নি MEMS, সেটাই বললাম।
তীর্থম সামন্ত, unmute yourself. Hello, unmute yourself. তীর্থম, তীর্থম, unmute yourself. Otherwise I need to remove you. Can you hear me? Okay, so clear up to this much. So I proceed to the next section.
Series of atomic moment of the diffusion.
Hello,
Two basic atomic diffusion.
hello.
Sir, my interstitial diffusion is not clear, sir.
Diffusion, actually the what is this process? It is used in semiconductor device to introduce, yes, to introduce certain control amount of
Six
dopants, okay,
dopants, yes, sir.
into the semiconductor to change the conductivity type. Okay, and how this diffusion works, you can consider any semiconductor device book, and from this way you can learn the diffusion process elaborately. Okay, it's a physics,
Okay.
simple physics. Okay, I have just reviewed certain things which will be needed to discuss in MEMS. Because using this diffusion we can create the p-type, n-type silicon wafer, silicon substrate. Okay, so that's why I need to overview, means certain review of certain things. Okay.
Okay, sir.
Hmm. Okay, proceed to the next section, next slide, which is called the diffusion in silicon. Basically our main substrate material is silicon. Our interest is in silicon. So diffusion in silicon is done from these three methods. Okay, one is uh, diffusion from a chemical source, which is in vapor form at very high temperature, or can be using this method as diffusion from a doped oxide source, silicon dioxide, this type of certain oxide can be formed. And this is the third, which is diffusion and annealing from an ion implanted source. So ion implantation, we will go through this technique after certain slide. Okay, one or two slide. We will discuss about the ion implantation. Okay, so here are the three process. You just know about the name of the methods or the main criteria. How can you diffuse the silicon? Okay, so these are the three methods. So basically diffusion and ion implantation, this is the opposite to each other. Okay, these are somehow related to this dopant concentration, means to control the uh, amount of dopants into the semiconductor, but there is slight difference. Now ion implantation, so that is another kind of technique by which you incorporate dopant into a controlled manner. So ion implantation is a process of introduction of ionized projectile atoms, which we call um, impurity, into targets, and the target here is silicon substrate with enough energy to penetrate beyond surface region of a single crystal substrate in order to change its electronic property. Okay, so that is the definition of ion implantation. Now how it is done? First, the dopant atoms are vaporized, then they are accelerated, and then directed at the silicon substrate. That means there are three steps. The dopant atoms are first vaporized. It has to be in vapor form. Then it has to be accelerated. So the energy of the impurity atom will increase. So after acceleration, then they are focused and directed towards the silicon substrate, where it will collide into the substrate and it will go deeper into the silicon. Okay, implant means deeper into the silicon, and that is the physical bombardment process, which is called ion implantation. Okay, so dopants enter the crystal lattice, collide with silicon atoms, and gradually lose energy, and finally coming to rest at some depth within the lattice. That is the process. Okay, so first collision, it will lose energy, and during after losing energy it will settle down at a particular depth on the silicon. That is the actually step. Okay, so it is implanted into the silicon. Now what are the specific features of ion implantation? You can get precise control over the number of implanted dopants, the control of impurity in ion implantation is of the order of plus minus um, 1% over the range of doses 10 to the power 11 to 10 to the power 7 ions per centimeter square. Okay, but in diffusion at best 5 to 10% at high concentration, and or at low concentration. That means what is that? You can get the control of impurity atom plus minus 1% in case of ion implantation. In parallel, you can see in case of diffusion, the control is 5 to 10%. Okay, so much more precise doping profile, much more control on the dopant atom is possible in case of ion implantation. What is the another aspect? It's a low temperature process, less than 400 degrees centigrade, where diffusion is a very high temperature process, and normal temperature range is 900 to 1100 or 1150 degree centigrade. And nowadays all VLSI process people prefer low temperature because of the out diffusion of impurity. Okay, and because of the problem of rearrangement of dopant atoms and further diffusion, which will clean and doping profile that people try to get rid of, and as a result of which low temperature process is highly desirable, and then ion implantation is one of the choices method of incorporation of impurity atom into the silicon. Okay, so why a variety of profiles can be obtained by controlling energy and dose, which is not possible in case of diffusion. Now, different kinds of profile you can get by controlling energy and dose. I will show some doping, some profile diffusion, profile curves in ion implantation, if possible, which will show you how the various kinds of doping profile you can achieve. So ion implantation is a non-equilibrium process. What does it mean? Non-equilibrium process. That means it can introduce impurity atom in excess of solid solubility, which is not possible in case of diffusion. So diffusion maximum dopant incorporation is up to it solid solubility limit. Beyond that you cannot do it, but in ion implantation you can do it. The impurity atom makes it solid solubility limit. That is why it is known as non-equilibrium process, and diffusion is not a non-equilibrium process. Okay, diffusion is an equilibrium process. So other points are um, their implantation, like implantation is conducted in vacuum. So you can expect clear and dry process. Dry process diffusion is not in vacuum. In normal atmosphere it is performed. So there is chance of incorporation of dopant in diffusion. Okay, so so there is a chance of incorporation of dopant impuritism other than the dopant atom. So it is a clean environment if ion implantation. In case of ion implantation, it is a clean environment, clean process uh, where this the dopants can be controlled. Okay. So next point is the implantation of energy, which rises from 1 kilo electron volt to 1 mega electron volt, resulting in ion distribution with average depth ranging from 100 Armstrong to 10 micron meter. Okay, 10 micron. You can get 100 Armstrong depth, diffusion depth, which is not possible in case of diffusion by controlling energy. So low energy ion implantation of the order of 1 kilo electron volt, 2 kilo electron volt, 5 kilo electron volt, you can have very shallow depth junction. So nowadays shallow diffusion are all made by ion implantation, not possible in diffusion.
Mm.
Okay. And on the other hand, if you use high energy ion implantation in the range of 1 mega electron volt, uh, you can get higher depth. Okay. So normally high energy implantation is required, uh, and those kind of things you cannot get in case of diffusion. So doses ranges from 10 to the power 12 ions per centimeter square to 10 to the power 18 ions per centimeter square. So those basically gives you the resistivity value, energy gives you the junction depth actually, and how much deeper you can implant the dopant atom, and concentration which gives you the resistivity or conductivity of the layer, that will be decided by the dose range. So it can range from 10 to the power 12 to 10 to the power 18 ions per meter, ions per centimeter square. Okay, but only one drawback in ion implantation is present. What is that? It results in damage to the semiconductor, but its solution is also there. Okay, what is the solution? Annealing at elevated temperature is necessary to heal some or all of these damages. So that is why ion implantation is followed by annealing, because during implantation some minor damages will be created and those damages will be removed by annealing technique, which is solid phase epitaxy. Last day I have discussed some of this annealing technique. So epitaxial growth is there, so this can be removed by this process. Okay, so so during the implantation process, because of the damage, the material may be amorphous in nature. And how do we know it just after implantation? If we go for the measurement of the register, you cannot measure because it's amorphous in nature, but after annealing it will be recrystallized. So easily you can get the single crystal layer, and then you can measure the sheet register by 4-point resistivity method. Okay, so that is one of the reason of ion implantation. And if you go for measurement of sheet register by 4-point resistivity method, you cannot measure this directly. Okay, so annealing is must. And in case of ion implantation, for removal damages and for recrystallization, as I mentioned, annealing is used. Restoration of electrical activity, because some mu, sigma, etc., all will be restored after annealing. Then furnace annealing causes appreciable redistribution of impurity, so people prefer for this RTA, which is called the rapid thermal annealing, and it is suitable for shallow junction. Now, two kinds of annealing are there. One is the furnace annealing, another is the rapid thermal annealing, or RTA. Okay, so in case of furnace annealing, it causes again redistribution of impurities, but in case of RTA, it means high temperature, very small time, maybe 1 minute, maybe 45 seconds, you can use for annealing at high temperature, say 800 or 900 or 1000 degree centigrade, so that the heal of the damage, and again it will recrystallize, and that is the that is preferred in iron implantation, followed by rapid thermal annealing. Okay, so next is the materials for MEMS. So materials are the fundamental things, or basic things based on which we develop various kinds of sensors while exploiting the properties of materials, and the materials are of different class, and all those classes little bit I will discuss in within few minutes. So the materials which are used for MEMS are basically from different groups. Some group belong to the metals or metal alloys. Some group of metals belong to semiconductor. Okay, particularly silicon and metals, and also metal alloys. Other than those, sometimes we use some ceramic materials also, and polymers materials also. So these are the four classes of materials which are used for making various kinds of micro sensors, okay, or MEMS based devices. Next is the metal and metal alloys for MEMS. So we use thick metal films for those devices which are used for structural materials for final sensors, and sometimes it is also used as a mold which has inserted into the polymer on ceramic micro molding. So what do you mean by micro molding? And what are the molds? So this is a technique by which you can make the mold or micro mold, that is uh, that is performed in actually micro machining techniques. Okay, so micro machining techniques will be discussed. It will not discuss now. Okay, that is in different module. I will not discuss right now micro machining techniques. So basically micro machining techniques, there are two types of micro machining: bulk micro machining and surface micro machining. How can you create the machining? Machining means you need to machine it in small size. Okay, so that will be discussed in at certain time. Okay, not now. So now other than this micro molding, there are other techniques which are mainly micro electroplating or photoforming. These are used to basically build thick metal film structure for different components of the microsystem or MEMS based devices. Now electroplating is the another technique which is used for making thick metal films. Thick means I want to say several microns, maybe 20 microns, maybe 30 microns, 40 microns, in that range. Okay, micrometer range, micro. So if you have to deposit more than 10 micron, then conventional the film evaporation technique, thin film evaporation technique can be used, or sputtering technique can it cannot be used because of certain disadvantages in sputtering technique. It is preferable if it is within deposit more than 10 microns, then prefer the thin film evaporation technique. With that technique, you can get films of the order of maximum 2 to 3 micron, and if you want more than that, 10 micron, 15 micron, and 20 micron, like that, then you have to add a certain technique. Those are mainly in discuss CVD techniques and the electroplating techniques. Now, electroplating technique is getting a lot of importance nowadays, because this particular technique is a low temperature process where the the chemical techniques are used, and basically it is electrolysis of some chemical solution, and we have to use the cathode and anode, and we have to supply some current to that electrolytic cell so that the chemical electrolyte will decompose, and some current and so there will flow some current and electrolyte will decompose, and there are some part that will be the metal, and the metal will be deposited on cathode. Okay, last day I have discussed the CVD technique. So certain metal will be deposited on cathode where the wafers are loaded, so that is a basic principle. And with the principle, we can have the metals of thicker films, for example gold or nickel or copper or chromium. Those are deposited by electroplating techniques, and various applications are there for the electroplating of gold, nickel, copper, etc. So copper material particularly is used nowadays in VLSI also for interconnects purpose, interconnecting purpose, because of very low resistivity of the copper material. So conventional techniques which are used for VLSI metallization are mainly the thin film evaporation technique. There are certain problems also, because of which copper cannot be evaporated in vacuum by resistive or electron beam evaporation, which is not possible basically. So electroplating is the only choice by which you can get the copper film on silicon or silicon dioxide, which is used for interconnection VLSI. But in case of MEMS, the materials used in electroplating are mainly chromium and gold. In addition, means chromium is used for addition of the gold film with the silicon or silicon dioxide uh, substrate, uh, which is a buffer layer, and basic material used for those purpose is gold. Now these are the techniques I have discussed. Another uh, is a 3D stainless steel micropart by photoforming. Another technique is 3D stainless steel micropart, which is performed by photoforming. So the stainless steel materials are also used for making 3D structure, three-dimensional structure. So you have so where this will be applied, this 3D microparts. This is applied in many actuators or many microsystems. Okay, so that which are made of steel that cannot be evaporated, that cannot be electroplated, that is formed by photoforming. Okay, which is the another technique. So that photoforming basic principles are how it is being made, the combinations of the it has the combinations of metal alloys, which is maybe cobalt, maybe nickel, manganese thin films, which are basically the magnetic materials. Okay, so this alloy, cobalt, nickel, manganese, is used for permanent magnetic material for magnetic actuation. So sensors and actuators, some part are sensor and some parts are actuator. And actuator principle are various kinds of principles are used for actuation. One such principle is the magnetic actuation, and for magnetic actuation you need magnetic material, and those magnetic material, one of the important material is copper, nickel, manganese alloy. So titanium and nickel are used for shape memory application. Okay, so this has tremendous application in MEMS and microsystem, and different actuators also. And this is used sometimes for sensing and actuating kind of application, which is known as shape memory alloy, SMA, shape memory alloy. And electroplating of nickel and iron permalloy on silicon for magnetic MEMS is also getting importance nowadays. Okay, so these are the various kinds of metals and their alloys which are used in MEMS or in any micro sensor devices. Okay, MEMS based devices. Okay, this meeting we have 2 minutes in hand. If it is disconnected, so everyone please rejoin using the same link to continue the second session. Okay.
Okay.
So now the polymers, I will discuss on polymers, and polymers are extensively used uh, in current scenario as both structural and functional materials for micro devices and MEMS. Okay, so polymer can be used as a structural as well as it can be used as a functional material also. And I will show you some table this here. So which properties are used for making functional layer or functional device, and which property of polymers are used for structural devices. So I will show you in the next slide. Okay, now the main properties used for polymers are elasticity, optical properties of polymer, biocompatibility of the polymer. Okay, so these are the main advantages of the polymer because of that it can be used as the structural materials for MEMS. Now polymer strain gauges and capacitors serve as a sensing element of piezoresistive and capacitive micro sensors. Okay, in these piezo sensors, what I mean, there also you can use the polymer material and can be used as a